Good morning. Today we are going to discuss about the remaining interview questions of VLSI DFT. What is transparent latch? Where we insert transparent latch diagram. So transparent latch is a storage element. It has an input and an output and an enable or a gate pin. When the enable is active, the output transparently follows the input with some small delay. When enable becomes inactive, the output freezes. It holds that value. Next one is draw the EDT logic, how decomposer compactor, how it looks. Majorly, EDT is used for the compression. So with the help of EDT, we can able to reduce the test time. So we have EDT technology behind the test compress. So based on the standard scan with atpg, deterministic pattern generation. Requires onboard test logic, decomposer, compactor, and bypass. This is decomposer, compactor. This decomposer consisting of a ring generator and phase shifter. So the ring generator will generate the pseudo random patterns. So these random pseudo random patterns are randomized by the phase shifter logic and then applied to the core, that is the block. And we have a compactor again it will compress it to the uncompressed scan channel. So the inputs for this one is uncompressed scan channels. So here those are compressed and again we'll get uncompressed output. So these are called the scan channels and these are called the scan chains. So we have decomposer bypass. So when we go with the bypass logic, this will uncompress the compressed logic. It has a EDT clock, EDT update, EDT bypass, scan enable, and scan clock signal. Scan enable, scan clock signal are used for the core logic. This is the core logic. And EDT clock, EDT update are both are connected to the compact decomposer and compactor. So suppose if we have EDT bypass is enabled, so we'll go with like this by bypassing the logic and reduce the test data volume. Actually, this will reduce the test data volume, test application time also. Yeah, decomposer logic will have a ring generator, phase shifter, eliminate the linear dependencies, generate the pseudo random patterns. And next, we have a data control signals like EDT clock and EDT update. Scan channel inputs and masking logic. Masking logic, whenever if any channel is propagating X, based on the masking logic, we can block it. Next one is XOR trees. XOR trees are there. Is it for these scan channel outputs? These are there. This is the masking logic. It is connected to masking logic. So these are connected to the scan chains. This masking bit is 0. This particular scan chain is blocked. It is connected to the output. And how did coverage analysis? By using the report statistic command, we will get test coverage and fault coverage reports. What is pipelining technique? Pipelining can be defined between the channel IO and pads. Channel IO and pads enable a very high speed test compress shifting, allows different channels to have a different number of pipeline stages. The help of pipeline logic, the speed is going to be increased. Pipeline. Why we need MBIST? Due to complexity of the memory architecture, the possibility of the OD occurring manufacturing defects is more. So hence memory is very challenging to us. Memory built-in self-test has been proven to one of the most cost-effective and widely used solution for memory testing. It allows for the robust testing of memories, reduce the test time. All the memories of the design can be tested in parallel, lesser the test cost. So what are different memory faults? How MBIST controller test those faults? Stuck at transition coupling faults. This one is a MBIST architecture. Draw MBIST architecture explanation. So this one is a MBIST architecture. So FSM, we have address generator, background pattern generator, which are connected to the mux, and this one is a memory, embedded memory. This one is a compactor, decoder is connected to FSM. There are the general questions. How many blocks in your SOC? 30 blocks. So how many blocks you work? 3 blocks. What is total flop count? It is around greater than 80K. Don't say 15K and 20K. How many test clock and functional clocks and their frequency? One test clock, 20 megahertz. 4 to 6 functional clocks, 500 megahertz to 1 gigahertz. How many scan channels, internal scan channels, compression ratio? 4 to 8 scan channels, compression ratio, 10 compression ratio. How you generate capture clock for a stacked test from IO pad? How you generate a capture clock for transition test from OCC? How you generate capture clock for stacked from IO pad? Is there any dedicated test clock in your device? Yes. Consider a total or draw for transition test each clock. These are the some of the questions. Okay, we'll discuss the remaining questions in my next video.